that uncertainty if we were to continue and add those values or multiply those values. Chapters 11.1 and 11.2 are sections are really valuable for your IA, but aren't really tested on the exam. So I'm starting in 11.3. So when I say we're doing chapter 11 and Emma says what's it called, I'm only giving her the name of that last bit in all of 21, which is going to be the spectroscopic identification of organic compounds. So because all organic compounds are, white crystalline solids, they're pretty hard to tell apart. Why are they all white crystalline solids? They're made of the same stuff, okay?
They can't be that different if they be equal to that.
All of the spectrum of the absorbed light.
They all absorb light in the ultraviolet region because we're breaking relatively strong bonds. So that's why they all look the same. So we're going to use other techniques to try to figure out what's going on. We do not own any of these things. So don't think I suddenly have a new IR experiment to do. All of these are available in a proper research lab in another place. So the four things that we're going to learn about in 11.3 and 21 are the index of hydrogen deficiency, easy peasy. IR spectroscopy, IR stands for infrared. It's the light that is just slightly less energetic than red light just south of the visible part of the spectrum. Mass spectroscopy. We learned about that in chapter 2 when we were talking about the isotopes of bromine. We said that we might see a peak at 79 and a peak at 81, and a peak at 79 would be just a little bit taller because the mass of bromine is just a little bit closer to it. We're going to now use that not for atoms, but instead for molecules. So we're going to watch molecules fragment, and so you're going to see a peak at a mass of 45, and you're going to be, yo, that sounds like a carboxylic acid, because if I add COOH together, that's 45. Or if I see a difference of 15, I'll be like, oh my god, I think a methyl flew off, because CH3 has a mass of 15. So we're going to use that same technique, but in a totally different way. You still do not need to know how any instruments work. For these two, I mean that very literally. For this last one, NMR, nuclear magnetic resonance spectroscopy, it is my belief that you need to understand a little bit about the technique before you can understand the data. So I will talk the most about NMR. If you've ever had an MRI of your knee, it's the same thing. They just deleted the word nuclear because it sounded scary. So we just call that magnetic resonance imaging, but it's the same M and R. We just don't say that because it's frightening. The nucleus that we are referring to is the proton, or the hydrogen nucleus, so it's not something crazy. It's just talking about protons in your body. If you think about the human body, there are a lot of protons because you are a very wet person. And as such a wet person, your bones have water, your blood has water, your muscles have water, your cartilage has water, and that water is trapped in different ways in those different materials. And an MRI looks at that. It looks how the water molecules are behaving in different, environments. We are going to be like as far away from that as possible. We're going to be talking about the hydrogens that are in organic materials. While organic materials aren't necessarily wet, they are full of hydrogens, and all of the hydrogens have different chemical environments. So we're going to talk about that. Bueno? There is shockingly little calculation. If you go to InThinking and you do all the practice questions, I will provide them all, don't you worry. A lot of them are going to start with, hey Moheb, this is an organic compound, and they figured out that it was 80% carbon and 20% hydrogen. And so he's going to have to go back in time and do the calculation, figure out the empirical formula of it. So that is a math that's in this chapter, but back to chapter 1. We'll practice it once. This is the other math I see. Again, it stands for index of hydrogen deficiency. What it's meant to do is count the number of bonds and rings in a molecule. Sorry. Number of pi bonds and rings in a molecule. So you might think of this as a degree of saturation. many more H2 molecules could I add to this molecule to completely surround every carbon with 4 bonds. Kind of reasonable? So you can draw a molecule and you can sort of answer what the IHD might be. One pi bond in that. But instead, what I'd like to see if we can do is take the formula for a molecule and try to get to that one. And so what I'm going to say is if I take 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2, I think that I should be able to determine that ethene has a single pi bond. So let's see if I mess this up terribly. I have 2n plus 2 was our formula for alkanes. So I'm taking the number of hydrogens an alkane should have on the left. I am subtracting the number of hydrogens that are actually there, and that difference should tell me something about how many hydrogens I could add into this system to completely saturate it. That's how I developed that formula. On the left, I have 2n plus 2, and on the right, I have the actual number of hydrogens. So let's plug in and see how we do. I get 2 times 2 plus 2 minus 4 divided by 2, 6, 4, 2, 1. Oops. So try it for propine. If I didn't mess up, it should be easy. The answer is 2. If I did mess up, you know. Let's see if I can do better.
Is it always that one?
No.
Oh.
Okay, for me, Elizabeth, honestly, it is always that formula because I am not smart enough to remember the other formula. But I just internet searched it, so you know I'm good now. I'm going to tell you what I honestly do, and I'll write down the real formula. It's your choice. This is not in the data booklet. So if we didn't mess up, we're going to take 2 times 3 plus 2 minus 4 divided by 2. 6 and 2 is 8 minus 4 is 4 divided by 2. It's not bad, right? The problem is that you learned quite a few different functional groups in your travels through organic chemistry, and I think you should be able to name some functional groups that contain atoms that are neither carbon nor hydrogen. So we have amides, which is going to add a nitrogen and an oxygen. Can you think of any other elements that we had to deal with in our roadmap? We also have halogens. And so what we've got to do is we've got to somehow take the formula that I've written down, but admit that these other elements could be present. So where would a halogen go in a molecule? So if I made a chloropropyne, what would the chlorine change in a molecule? Yeah, it's just going to behave exactly like a hydrogen. It's always terminal. And so if I wanted to make this formula better, what I could do is I could say that I'm not going to subtract the number of H's. I'm actually going to subtract the number of H's plus halogens. Reasonable? So my strategy is not to remember that, but just whenever I see a halogen, to turn it into an H. I will physically cross it off on my paper and write an H above it. Because again, I'm not very good at this. It's not that interesting to me. The formula gets bulky with 5 different variables in it. But as long as you have this thought process that a halogen is really no different than a hydrogen, it sticks on the end of something, you should be good. How about in ethanol? What is the IHD in ethanol? 0. There's no double bonds. How about in propanone? So now what I want to do is I just want to put my hand over the O. What is the IHD if I had ethane? Still 0, still boring. Okay, what is the IHD if I have this molecule I can't make? I have 1, 2, 3 carbons, so I'm going to take 2N is 6, plus 2 more is 8. I'm going to subtract 6 to get 2 divided by 2 is 1. So whether I have the oxygen or I don't have the oxygen, I'm getting the same answer. Oxygen is everyone's favorite. It doesn't affect the calculation. It's because oxygen comes with 2 lone pairs, so it's kind of like satisfied. Like if you think of what a happy carbon looks like, it looks like it's got bonds on both sides of it and an H up and an H down. The oxygen is always going to form 2 bonds, but it's got a lone pair up and a lone pair down. So it's not going to change the number of carbons, it's not going to change the number of hydrogens, it's just going to be there. So IHD doesn't actually include oxygen in the formula, so we're good. We've taken care of C, H, O, and X. That means we have N to go. So that's not your amide, because I'm just not that ambitious right now. But I drew you an amine and I drew you a nitrile. Nitrogen has 1 lone pair to kind of make these 2 things related. What's the IHD in propane nitrile? 2. I have 2 pi bonds. And what's the IHD here in the amine? 0, because I have a completely saturated molecule. There's nowhere that a hydrogen could go. So this is a little bit awkward. Yes, ma'am. 1 and 2. Because it's a triple bond, it's 1 sigma and 2 pi's. So the triple bond has 2 pi's in it. So this is a little bit awkward because, like, if this were a carbon, it would have 3 hydrogens. And as a nitrogen, it's only going to have 2 because of that lone pair. And so the formula 2N plus 2 isn't going to work out quite right with nitrogen. And so my approach is to, whenever I see a nitrogen, cross it out and call it a CH. The reason that I call a nitrogen a CH is because a nitrogen is a big atom, like a carbon, nitrogen, oxygen kind of thing, something that can make bonds, and it has a lone pair. The H that I'm writing here accounts for that lone pair because the nitrogen is not allowed to make connections. So if I did that and tried to apply this formula, I would take 4 carbons now, minus 3, 4, 5, 6 hydrogens, divide that by 2, and I would get 2, which is the answer that I expect. So my strategy is to take a nitrogen and replace it by a CH. If you wanted to use the same strategy for oxygen, you can take an oxygen and replace it by a CH2, but I've had more success with saying, hey Luke, just ignore the oxygen.
Do we have to use this one, or like, because like we just look at it and we know the functional group method?
So the issue is that when we start these problems, typically what's going to happen is I'm going to tell you the percentage of carbon, hydrogen, oxygen, and potentially nitrogen. You're going to come up with an empirical formula. You're going to use a mass spectrum to determine the mass of the molecule. And so now you're going to have an empirical formula, a molecular formula, and you'd like to know what functional groups might be there. Are you trying to find a ketone or an aldehyde, or are you looking at an ether or an alcohol? Is there a double bond? And so this is when you can't draw the molecule, instead you just have a formula for the molecule. So we're going to try this for some big molecules and look in our data booklets to see if we get them right.
In those problems, you say like ether or alcohol. You don't pick one, right?
I mean, you're going to have more information that will relate more of it, but it's just to limit what you're looking at so that you're not trying to find evidence of an aldehyde if you know there's not a double bond. So again, this is the only formula I know because it's the only one I can keep in my head. But if you want the full formula, I did look it up for you. It's going to be 2 carbons plus 2 minus the number of hydrogens minus the number of halides plus N all over 2. That's like one too many things for me. I don't know how you feel. It's not one too many things for you, clearly. I can't retain it. So the other choice is replace X with H and replace N with CH and do 2C plus 2 minus H over 2, which again is just that 2N plus 2 rule that I saw with the alkanes. So let's see how it does. If I can type. So penicillin has the molecular formula C16H18N2O4S. I'd like to know what you think the index of hydrogen deficiency is for penicillin. Now our first problem is that penicillin is a sulfur-containing thing. Do you have any strategy using the periodic table that's going to help you figure out what to do with the sulfur? Because I didn't talk about it because it's not the thing in the book.
Just the oxygen.
I'm just going to pretend that's an oxygen, so I thought it was doable.
So we pretend that the sulfur is an oxygen.
So I'm just going to, like, yeah, why not? Shows it because I was relatively sure it was here. It is. Francesca's using a calculator, so I'm going to trust her. I'll use a calculator too. I'll cry. What'd y'all get? Got 9 too. Why the heck do you think you got 9?
Oh, are we not in here? Is it too big?
Yeah.
It's not 9 as well. Is it more already? Should we have put missing info?
It is not correct. Never mind.
What's not?
Thanks, everybody.
The formula's not correct?
I searched penicillin. It gave me penicillin G. For those of you who want to be doctors, that's not straight up penicillin. So I'm going to try to show it.
So is 9 right for penicillin G then?
I'm going to show you. God bless. I chose something that was in your data booklet so that you could check for yourself, right? And then I Googled the formula because I didn't want to count in the data booklet because I'm not good at counting. And then I apparently looked up penicillin G because I am not familiar. I am allergic to penicillin. I am not an expert in the penicillin game.
Why are like all results
They also don't use penicillin anymore.
Amoxicillin is what I'm allergic
They
to.
don't use
Both my
penicillin.
parents are.
Yeah, they only use it for the worst case
So
scenario.
is my uncle.
It's mainly how prevalent.
So my allergy is not life-threatening, so when you become a doctor and you decide that I need to take it, just give me a lot of medicine to make me feel okay. The good stuff. But it got to the point where if Joseph took it, I would react to him. So we have a no one in the house can have this kind of policy. I've reacted to Keith having it. It's all bad.
It's all like penicillin or?
Amoxicillin. What?
When you have a worse reaction to penicillin, then is there any
Yes.
exam?
Okay, so this is the molecule that I asked you to calculate. You'll see that this is benzyl penicillin, so that's why the number's so big, because we threw that benzene on there. We weren't planning on, so benzene's big. So you guys are gonna help me count rings and double bonds. So it might be convenient if I didn't draw benzene like that. So how many double bonds are in benzene? So I'm gonna take the ring that we're used to drawing and just resolve it back into 3. And so I'm gonna count double bonds, 1, 2, 3, 4, 5, 6. And I'm gonna count rings, 1, 2, 3. We're not dumb, I just don't know how to Google. Let's try something less ambitious. Oseltamivir. Anyone know what that is?
What does it end
I thought Rita wasn't in this class.
with?
My grandma is
Oseltamivir. Treats influenza. It's an antibiotic. It's Tamiflu. Have any of you done Tamiflu?
Yes.
So if you react really poorly to the flu, sometimes you can go to the doctor early and feeling sick and they'll give you Tamiflu to fight the virus. Okay, so the formula of it, because I assume you don't know, is C16H28N2O4, and I'd like you to calculate the IHD, and then check your work. It's on page 39. I'll check my work. 39. Oh, I thought you wanted board.
Yeah.
No one wonders how many things I can get wrong in one day sometimes. You get 4? Good. And so if you look at it, can you see that there are 4 rings and or double bonds in it? So again, I find this strategy convenient. You can memorize that if you're good at memorizing. I'm quite shy at it.
Like, we just ignore O.
Yeah, you can replace it with a CH2, thinking about it as having those 2 lone pairs, so you do the same thing to oxygen and nitrogen. Nitrogen you place with a CH because it has 1 lone pair, oxygen with a CH2 because it has 2, or you can just straight up ignore the oxygen.
Then why let's
Okay,
Here's the answer.
4.
2 from 16 and then 2 from the nitrogen, the 2 and then minus 28 and then 2K.
So I hope this didn't feel awful. It's just supposed to be a quick way to figure out if something has rings or double bonds. Certainly, if you're getting an IHD of 4 or more, what do you think is probably in the molecule? I think benzene is in the molecule. So if you're getting an IHD of 4 or more, it is probably true, because we don't have molecules this big in our real life. Like, you don't know how to synthesize that. You know how to synthesize, like, propanone. So it probably has a benzene.
Why did we add 3 to the index value for last There were 6 double bonds and 3.
Because the penicillin that was on the internet was different than the penicillin that was in your book.
Oh, but the answer's still 9.
The answer was 9. Yeah, like I just had a moment of thinking I Googled right and I didn't practice Googling, I guess, before class. I thought I could handle that. I'll think of it, again, next time. Okay, so you're now experts at IHD. It does not get any harder than that. You've solved problems that are absolutely as difficult as the most difficult problem you would ever be asked. Sometimes there is a singular multiple choice question that's like, hey Mohab, this is the structure, what's the IHD, 1, 2, 3, or 4, and he circles the right answer and he's done. IR spectroscopy is an awkward thing in our life because there's a lot of theory to it, but ultimately what they expect of you is almost nothing. So IR stands for infrared. I'm looking for the right page in the data booklet. It's page 25 that we're going to be focused on. And this is where you're going to find your infrared data. The notion of spectroscopy in general is that it's the interaction of light and matter. So when we talked about UV visible spectroscopy, which wasn't a whole lot, probably back with the Bohr atom, what we saw was that visible light was enough energy to take an electron in one shell and move it to another shell. It's better if you see the tape on the floor, but you know, you can imagine it. So generally, visible and UV light are responsible for the motion of electrons. When you go to the beach and you're in that UV light for a while, it convinces your thymines to dimerize. That's what the sunburn comes from. Your little cells are like, uh-oh, I'm damaged. I'm gonna apoptose myself.
What is that?
So when you make a dipeptide out of two amino acid units, that's a dimer. Two of the monomers are there. So it's taking two things that are more or less the same and having them come together to be one
Why
unit.
would it?
Why the cell knows that when the little DNA replication enzyme comes along, because the two T's are now linked together, it's going to read them as one. And that is bad because you're going to have off by one error, which is a frame shift mutation in your DNA.
So that's where.
And so your cell, like, so some signal goes out that's like, hey guys, we need to give this up. We're no longer copyable. I'm making up biology words in real time.
No, I don't know.
Okay, good, because like I'm done, like this is everything I know about it, so we're done.
Is infrared one line?
Infrared is one word in my culture, yes. I don't know, I think you probably could put a hyphen in it, but I would write it as a singular word.
And then you said what is the beach like?
So the beach was just about why UV rays are so bad for your skin. It's because they are changing the bonding, because they are moving electrons around. So they are taking the two T's that happen to be adjacent, moving the electrons enough to create different bonds, and that is why we sunburn.
Okay. Is that gonna be a
The idea is that you already know that electronic transitions happen in UV light, kinda, sorta, a real life example-ish. X-rays, what happens at the dentist's office when he takes an X-ray? He gets out the room, that's what happens.
Oh, yeah, also that.
So, X-rays are very high energy radiation. They can kind of blow apart molecules. It's not good for you to be exposed to too many of them. So this is taking like core electrons and moving them about, as opposed to valence or bonding electrons and moving them about, as we were with UV. So that is the distinction when I put in more energy. If I use less energy, I'm not going to be able to move electrons around. I'm not going to be able to break bonds. Instead, what I'm going to be able to do is to stretch and bend them. If I put in even less energy, that is the Greek letter. It goes by a lot of names. In America, we call it mu for mu alpha theta. In the Philippines, they call it mu because they're somewhat cultured. But in modern Greek, I have found we call it mi. So all of you who are in mi alpha theta, there you go. So that is the prefix that means micro, like micrometer, micron. And so that is how we write microwave a lot. Do you know what microwaves do to your food?
But radiation, like
They actually rotate it. It just makes the little molecules start spinning. I'm such a happy little molecule, I'll just start dancing.
It's not my blood.
I want that
The microwave
gift.
too, though. It's like, watch clean what it's actually doing.
There's gonna be a lot of me acting things out. Radio waves actually can't break bonds, stretch bonds, rotate molecules. They can't do a whole lot, but what they can do, we'll find out, is that you guys don't know this. You know how electrons have spin? And so you can have an electron, it can be like spin up or spin down.
They change
I don't really get it. Maybe
Protons have spin.
I don't get it. Maybe you should spin again.
Exactly. Radio waves will change the spin of a proton.
I'm gonna now forever remember that microwaves spin the electrons.
I'm glad that public embarrassment is the tool of remembrance. So which way is energy going, which way is energy increasing on my picture?
Yeah.
Energy is increasing up.
Yes.
So in this class, we're gonna talk about IR spectroscopy, that's this. We've talked a little tiny bit about UV-vis spectroscopy in the past when we do chapter 13. We will come back to UV-vis spectroscopy. We'll talk about electronic transitions in colored compounds. We'll also do this in biology. We'll talk about why chlorophyll and hemoglobin and keratin are all colored. So we'll learn about why those things become visible as opposed to UV. We will not talk at all about microwaves aside from me dancing for you. But radio waves are going to be what we use in NMR. So NMR is a fantastically safe technique because the energy that you're being exposed to is extremely low. So you can have as many NMRs done to you, MRIs done to you as you care to. Marashi?
So the difference between UV and X-rays is that they both change the electrons, but X-rays change the core electrons.
And UV changes the valence electrons. Okay, so we're gonna go back to infrared and we're gonna look at stretching and bending bonds. And so as Quinn well knows, it's our token physicist, right? We're gonna model bonds as springs. And he probably knows more about springs than any of us, so we're just gonna keep this as low-key as possible. I'm gonna tell you a few things. I know that Hooke's law tells me that there's a relationship between how hard I pull, the force, and how much this thing moves, the displacement if you want. And this thing is called the force constant. You in your infinite wisdom are applying this to a series of molecules that could have carbon-oxygen single bonds like an alcohol, carbon-oxygen double bonds like an aldehyde, or if you really wanted it, some carbon monoxide. How do you think the spring constant would be related here? Yes, I think it's gonna increase. So the spring constant, while I'm sure that we could learn a lot about it, is really just a fantastic way of talking about the strength of a bond. Generally, we're only going to see really strong differences as we change a bond from single to double to triple. But there's another formula that I know about springs that I don't think you need to know, but I'm going to write it down because that's how we play. And it says that there is an oscillating frequency of a spring, and it is given by a ratio of that force constant to the mass. It's actually the reduced mass, I think, but Quinn can tell us if I'm lying. This is just like the resonance frequency. This is just like how that spring wants to be going. So at the top, we have how strong is the bond. And on the bottom, we have, well, what's attached. So if you were to take a second and look in your Fly little data booklet, you're going to see that you have bonds CI, CBr, CCl, and CF, the first four that are listed in the table. What do you notice about the wave number, that's a word we haven't said, but just ignore the units, pretend it's the same as what I've got on the board, I'll defend it in a second, just ignore it, nobody cares. What do you notice is changing? Is it increasing or decreasing? So if I compare CI, CF, and I look at some number that apparently I think is related to the frequency, because I'm not lying to you, this one's at 490, and this one would be around 1,000. So as Elizabeth says, this is increasing as the mass is decreasing. Is that consistent with your understanding of algebra? Excellent. So one of the things that's kind of weird is if you have a hydrogen, what happens to this frequency? It's going to be super high. If you have a double bond, it's also going to be kind of high. So the two things that would make the frequency high is having a hydrogen attached and having a multiple bond. So let's see if I'm crazy. I'm going to look at CH.
Which section are we in right now?
Section 26, page 25, 11.3 infrared spectroscopy. It's all the way up in the 3,000 range. So as Karthika said, like when we want really big numbers, changing one of these things that's attached to the spring to a hydrogen is going to have a big effect. In fact, it has a bigger effect than putting a double bond in. A carbonyl is going to arrive around 1,700. Do you have to memorize any of these numbers?
No.
Not a single one, right? Like you get the data booklet. Do you think they expect you on paper one to know any of these numbers?
No.
They do not. So far, so good? Okay, so the frequency there is the unit that I learned physics in, but like IR spectroscopists have like a crazy sense of the world. What we're going to find is that bonds can absorb light of a frequency that matches the square root of k over f, like of a given frequency, the frequency that's in there. And so we're going to find that frequency, omega and nu are slightly different. One is an angular frequency, one is not. I don't care. There's a 2 pi difference. No one's plugging in any numbers. They are directly proportional to each other. So what are the units, pray tell, of frequency? Reciprocal seconds? Hertz? Take them both. How is that okay? Either one's. What is energy in terms of frequency according to Mr. Planck?
Lambda. Oh, yeah.
Planck, that's in your data booklet. You don't need to know it. But I would like to consider maybe not having frequency in there. I'd like to consider instead having like a wavelength in there. Is there a way that I could get wavelength in there? I really understand wavelengths, distance between two, troughs or crests or whatever. Okay.
E over nu. No, maybe.
So the speed of light is the product of the wavelength and the frequency. So I can plug this into here and tell you that the energy is equal to hc over lambda, or it's equal to h nu. Is that cool? I mean, I'm just like showing you things you don't particularly care about, right?
Really trying to remember this.
I mean, I feel it. So I gave you everything over there in frequency, but the IR spectroscopists, they really like things in units of reciprocal wavelength because they hate you. We have a symbol for reciprocal wavelength. It's the Enya of the Greek world. It's a good Spanish joke. Anyone who's not getting it, ask your neighbor. We call it nu tilde, but apparently in modern Greek we call it ni tilde. We are always going to report this number in reciprocal centimeters. We refer to this unit as a wave number. And whenever you look at that disgusting unit, feel free to think of yourself, oh, they mean energy, or oh, they mean frequency. You do not have to do any calculations to get there. I just wanted you to see that there is a proportionality between an inverse wavelength and a frequency, and both of those are proportional to energy. So it's not my fault that all of this will be reported in wave numbers. It's just a perk. You're welcome. Wave number is the same as frequency if we're just talking about what's big and what's small.
When you said the bond strength increasing, what else, is it the springiness?
Yeah, that's the spring constant, how hard it is to pull.
Oh,
Okay, so I will do better on wave numbers tomorrow because that went over really poorly. But you know, I've got part of my graph. So an IR spectrum is going to have wave numbers. All of the numbers in your book, data booklet, are in wave numbers. You will never convert into or out of them. Here's the next thing that's going to surprise you. I'll put the big numbers here. I'll put the little numbers here. Because you got to read the same graphs that they publish. This is just what it looks like.
Doing it like that.
Okay, so I know that a bond is supposed to absorb frequency that matches its resonance frequency, that makes these bonds sort of start vibrating. Or we have multiple types of vibrations. And so the way we're going to look at that is we're going to shine light at these molecules, IR light no less. And if there is nothing that absorbs, the transmittance will be either 1 or 100%. There is nothing there. But if we find an absorber, not all of the light will go through. And so you will see what we lovingly call a peak.
Is this like the little box thing, but on the
I have no idea what that means. Oh, so the box thing is UV vis. This is a different color, so you have a different source. But yes, it's the same thing. And so that is my cartoon infrared spectrum. Again, no light will be absorbed if there are no cool bonds. But if we have a bond that is resonant with some frequency of light, we will see that it is absorbed by the molecule, and as such, less light is transmitted to my detector. So this is just like how much light I see on the other side. We will find that frequently we have something around 3200, something around 1700, and a whole bunch of junk in the 900 to 400 region, maybe 1200 to 400. This graph is frequently not linear. We're now going to try to identify what's present in this molecule. Pray for us all. You're going to notice, perhaps, with my poor drawing skills, that one of the things you see is that the peaks have different widths. You see that?
Yeah.
So this peak is quite narrow. This peak is pretty broad. These peaks are quite narrow, but they're weaker. So this would be a strong absorbance, and this would be a weak absorbance. So when I'm looking at this table, you might see the words strong and broad, weak. That's what I'm trying to cartoon here. You're also going to see that everything comes with a range. The way I've drawn this, you'll frequently see a little skinny thing on there as well. That actually represents two different bonding groups in the IR. So with a peak around 3200, can you identify what your best guess is? I'm guessing that this is mostly due to an alcohol with hydrogen bonding. How about the little like extra, less wave numbers than 3200? So some small, thin, but strong absorbing peaks. What do you think they could be given this table? That's a CH, that's right. So those little lines are frequently going to appear at the same place because they're also in that 3000 kind of range. If I have a really big envelope, sometimes I can see a little CH action. But if I have something that is broad up here, I'm still going to guess it's an OH. Yeah, whatever. The next peak that I have for you appeared around 1700. What do you think that's going to be? And then I have a lot of action between 1200 and 1400. It's frequently impossible to look at that and know what it means. We refer to this as the fingerprint region. If I took a DT's fingerprint, I could prove that she was a DT by comparing it to one that was already on file. But I cannot look at a DT's fingerprint and say, oh, I know who that is, right? A fingerprint is a way of comparing things, but it is not a way of identifying things. So if I already knew this molecule, so if I had a book, I could look in this region and say, yeah, it's probably that. But it is very hard to make positive identifications over here. Sometimes you can see the C single bond O. Sometimes it's a little bit like pulled out. And so you'll be able to see that at around 1050 to 1410, so we'll put this one at 1100. There's a peak that might be of some note, but it probably wouldn't be enough to prove to Brecken that it had to be a CO. I would have to know that there was an alcohol to be there, yes. Yes. So what you need to be able to do is look at an IR spectrum, pull out the bonds that are present, and then maybe try to construct them into a molecule functional group. A molecule's functional group. So here, you notice that I have a C single bond O. I'm not totally sure about it. I have a C double bond O, and I have an OH. Do you have any thoughts about functional groups that might match that set? What? So I'm hearing it could be an alcohol and it could be a carboxylic acid. So we have two choices here. I think we could believe that this molecule had these features. It had a C double bond O, a C single bond O, and an OH. Carboxylic acid. But Audrey could say, well, the OH in a carboxylic acid is supposed to appear between 2500 and 3000. And she's not convinced that this is at low enough wave number to support this idea. So there are two things that Audrey's going to have to do. She's going to have to solve the rest of the problem to see if there's information that will help her, because these boundaries are like the 60% of the time it will be in this range, and 20% of the time it will be smaller, and 20% of the time it will be bigger. So you cannot discard Q based on the fact that I put this at 3200 instead of 3000. So we would hope there was another piece of information. Our hope is that we're describing one functional group, not a molecule that has two functional groups, because we would like to keep things easy. There's no guarantee of that. I can find the hard problem, but generally we're looking for one functional group.
Yeah, I was gonna ask, like, there's all the squiggles between 1200 and 400, how do we know it's not anyone?
We don't. Traditionally, we've done a problem already that gives us some aspect of the empirical or molecular formula, so we'll know what atoms are present. I hope you're very quiet. You're on your computer. I don't know if you're doing the right things today.
He's got the.
I don't think so. It's all messy.
What do you mean?
So you're telling me that you're doing the right things? Does this seem doable?
Maybe like if I reach enlightenment early. Never forget to do this.
So let's see how I did. Let's see if we can. So here are some other comments that I think you should know. Not every vibration in a molecule is visible. For a vibration to be visible, it needs to change the dipole moment. So if you had a molecule like bromine, bromine only has 2 atoms. It only has a single bond. The only thing that can happen is the bond can stretch. There is no dipole moment here. There is no dipole moment here. There is never a dipole moment. Bromine will not appear in an IR spectrum. But water,
Induce a dipole moment.
it has to change the dipole moment. Water looks like that. So water has a dipole moment because the hydrogens are, facing you and the oxygen is negative facing me. And so if we did a nice little bend, bigger dipole moment, smaller dipole moment, bigger, smaller, it's changing. If we did this kind of a thing, we call this an asymmetric stretch, we're going to have a dipole moment that's, if we did a symmetric stretch, we're going to have a dipole moment that's changing. There are lots of different motions that this can do that are vibrations. For a nonlinear molecule, there are 3n minus 6 of them.
Wait, what?
For a nonlinear molecule, there are 3n minus 6 vibrations. So for H2O with 3 atoms, there are 3 vibrations. I did them for you. They are the bend, the symmetric stretch, and the asymmetric stretch. Really good at this. For a linear molecule, fun fact, there's actually one more. And so you might think to yourself that this molecule has no dipole, should not appear in an IR spectrum. That would be true if you were doing the symmetric stretch, but it would not be true if you were doing the asymmetric stretch. These 2 sides are different from each other. They don't cancel anymore. You'll see it. You'll also see the bend in this direction and the bend in this direction. You'll see 3 lines. One of the bummers of this is that water and carbon dioxide are strongly in our environment. So if you want to become an IR spectroscopist, you have to find 50 ways to deal with the fact that you do not want, air in your sample. So my thought process in giving you these formulas was to go back to that terrible penicillin that we started with. It was really big, right? I don't know if I can find it super fast, but it seems like maybe I could. 16, 18, 34, 36, it had 40 atoms. 40 atoms. So 40, it's not linear, is 120 minus 6, that's 114 vibrations. How many of them can you pick out? Just what's in this table, right? Like, what we find is kind of magical about IR that I don't know that we could have predicted is that it's not so much a collective molecular experience. We really see like flashing lights that say, hey guys, I've got this particular bond. So it's really nice that it identifies specific bonds in a compound. The downside of that is if Quinn gave me 1 propanol and 2 propanol, could I tell them apart? Just for ribbon. Because they have the same atoms bonded together. I have a carbon-oxygen bond, I have an oxygen-hydrogen bond. I know that the molecules are different, they will have different fingerprints, but when I pick out those key and very few peaks that I'm able to identify, I can't see a difference. Yes, ma'am?
What is the N in the?
N is the number of atoms, so you subtract 6 because there are N molecule, or N atoms, and they can move in the X, Y, and Z direction, so 3 degrees of freedom. But if all of the atoms move this way, that's translation. Same if they go that way, so that's minus 3, and then you can rotate around 3 different axes, so that's the other 3. This guy can't rotate around this axis, so he gets an extra bend.
What does it mean, like, number of vibrations? Is that like the little spikes on the?
Yes, but Although you may not see, well, in penicillin you would see all of them, but that's why the fingerprint region is so disgusting. And we don't even try. Please don't try, you can't do it.
Wait, so why can't we see the difference between one and two? Like,
Because they have the same bond. So all we're able to do is identify what bonds are present, and both of those have CC, CH, CO, and OH bonds.
So all isomers would be the same.
All
Isomers like two different.
All positional isomers and skeletal isomers would be the same, but functional group isomers would be different. I'm trying to use that language coming up in the syllabus for my sophomores. They're gonna put a little more of that language in, I see.
functional isomers?
So if you take a coup and you turn it into a kook,
How is it isomers?
they have the same formula. They have the same molecular formula.
Wait, the N means number of atoms?
What? N is the number of atoms. You do not need to know those formulas. I just wanted you to have a sense of like why things get complicated and what you can actually see. When Audrey goes back and she sees all the past paper questions, she's going to find some questions about why does HBr have a signal and Br2 not? Signal. Why do you see HBr and IR spectrum but not Br2? The answer is going to be because of the dipole, but then Karthik is going to be like, Audrey, they took that off of the syllabus in 2016, so watch yourself. So a lot of study materials still call that the forefront, so I thought I should say it out loud, but there will be no questions about it. I sent myself some spectra. I logged out of Outlook. I'm back in Outlook. I'm on the right computer. Probably want to download this. You'll see it eventually. Rohab, do you think we missed anything? You seem super bored today, so I thought I'd ask. Okay, so to grande. So you'll see that they use the term frequency here, but give you numbers and wave number. Again, that's because they're proportional to each other. Absorbance, what's the 0.1 here and the infinity there? That's because they took a log. The difference between transmission and absorbance is a log. I do not honestly care what they write here. Every IR spectrum is going to have dims. We still often refer to them as peaks because we don't have another great word for them. If you were looking at this peak right here, around about 3,000, what do you think it most likely is? So this is broad, this is not broad.
OH, and then.
This is an OH, these are CHs.
Oh.
So when I say broad, I'm looking for something that looks like a nice normal distribution. I don't mean that there can't be a whole lot of things on top of each other, and I feel like I've never been really good at expressing what broad means.
So then,
Smooth,
will the
wide.
Will the CHs only branch off of the OH thing? Because like in the example that you.
Yes, in my example, they branched off. In this example, they didn't. Here you can see some CH action right there. This is an OH, this is another CH, but it could be an NH, we're not sure.
But CHs can like have their own separate
Yes.
like gen.
Does NH look the same?
NH is paired, it looks the same, and it's usually a little bit to the left.
And
I don't expect NHs in your world, it's a prayer, but I don't expect.
we identify the bonds based on like whether or not like they're like on this side or like that side, or is it like just like a shape of
It's
it?
the shape and a location. So here in the 3000s with something broad, it's an OH. Here in the 2000s with nothing so broad, it's probably a CH. What doesn't this molecule have? So that will be a question as well. What is absent? It does not have a C double bond O. It does not have a C double bond C. This is not an alkene. It is not an aldehyde. It is not a ketone. It is not an ester. It is not a carboxylic acid. Over here, I'm hard pressed to figure anything out without some more details. When I look at this one, what do you notice about the envelope here in the 3 to 2000s? It's very broad. So this is what very broad might mean. The last one was broad. This one is very broad. But you see the structure, that's because there's some other stuff underneath it. I don't like that one. How about this one? What does it not have? It does not have an OH. It has nothing broad over here. But around 16 or 1700, we start to see something. It looks like it's at 1650. So it could be the C double bond O. It could be a C double bond C. It probably is a little bit closer to C double bond C. Would a benzene show up at C double bond C? No, because the bond strength is different. It's a 1.5 bond. This could be a piece of evidence. We just didn't know it when we talked about benzene.
So then how do you differentiate a C double bond C and a C double bond?
By their location, a C double bond C should be in the 1600s and a C double bond O should be in the 1700s. But again, all of those things are going to be with a grain of salt.
What the very far left beat?
CH?
H and then the thing on the top. That.
Somebody sneezed? I don't know. Do you see us getting very fine detailed in this, or do you see this pretty loosey-goosey? So we are going to have 3 pieces of information plus a molecular formula to try to decide what the structure is. So frequently, I don't really love this. I do kind of love it. I don't know. I'm kind of indeterminate on this. This is my least favorite of the techniques. Like, I feel like that should be a coup. I feel like it is very broad. But like, I'm a little bit burnt on maybe being wrong once, that I thought something was very broad and it wasn't. So I'm gonna make a little note in the margins that's like coup question mark, and I'm gonna flip to the next page and I'm gonna look at the next piece of evidence. If I see evidence of something that has a mass of 45 being able to fall off, I'm gonna be like, ooh, that's the mass of a coup. I'm gonna go back to this page and be like, heck yeah, that's a coup. I'm gonna look in the NMR, I'm gonna look for a signal around 11. If I see one, I'm gonna be like, yes, this is a coup. I strongly advise you, with all parts of me, not to feel like you have to do this problem linearly. Lots of IB, this problem doesn't depend on that problem, but in this unit, there are 3 pieces of evidence. You want to synthesize them and take advantage of the ones that you think are more selective. Are we having fun yet? Or is it Wednesday? Like, Wednesday should be a good day. Why is it such a poor day?
It's an okay day.
Yeah, you seem good today. I mean, I thought you were going to beat Mr. Morgan, and that's good. I like to see that part of you.
Are you all gonna what?
Beat on Mr. Morgan.
Beat specifically?
No, I don't think you'd ever lay hands on him.
I mean, he asks for a question a lot, it's a bit annoying, but
Yes, he acts a little lot.
I don't want it. Doesn't do it to other people.
Oh, you feel like it's targeted?
Yes, he does.
As to what?
But remember when we had like a club meeting, like leadership of BSU, and he came to us and he was like, what would you do if someone who isn't black tried to do BSU? And I was like, okay, it's a safe space for black students and they get my and then he sat there and was like telling us, okay, then what defines black? Like the whole time we had the meeting, I guess like, I
We
don't
had
know,
this
just
conversation in math one time.
because he knows what we mean by like black or like white. Like if we don't mean this by white, we don't mean this by black.
No, he knows, he just likes to like,
He plays devil's advocate a lot. Like, he wants to make people think more than he wants to be right. He just likes to say things to make them think.
yeah.
He said a lot of things. That's like, that's a little crazy in math. And then he like ends the conversation by saying, I just want to say something. I don't believe those things are black. Like, we had a bit of a conversation.
But we had
And
Kyle.
he like actually makes it really good. I never thought of color. He's like,
I think he used to have some weird views when it comes to like, who was black.
it's just like a tricky line because like he still comes off really bad.
What?
No, he does. But he doesn't say that.
It's true.
There was a point in time, no, there was a point in time where I was like,
Okay, so if it would be possible for us to do the homework, I would be all for it. Y'all are gonna help me with this. Identify the bonds that give absorptions labeled A, B, and C in the infrared spectrum of ethyl ethanoate, which is a kook. Why don't I have something broad over here? Because I don't have an OH. Excellent. I do have something skinny over here in the 3000, so I do know what it is. That's a CH. So when I answer the question, I do not say alkane. When I answer the question, what do I have evidence of, I give the bond. I know, I'm just saying it to everyone because I want you to. Okay, I have a big peak at 1700. What's that one? And I have a peak at 1200. And do you see how they picked it out of the fingerprint? I don't know that I would have known that that was the one I wanted to target. I don't know that you would have known. But if we believe this to be a kook or an ester, then I know I have to have evidence of why it's C. What's C? That's a C single bond O. And so these things together, a C double bond O and a C single bond O with the absence of an OH is going to be, hey guys, I think we have an ester. Could you draw something that wasn't an ester? Yes, if you wanted to. But we're going to try to do the simplest thing before we have to make life more challenging.
The characteristics of a C single bond.
A C single bond what?
2 carbons with a single bond.
2 carbons with a single bond. There are thousands of them, so we don't talk about it. It's in the fingerprint region.
Do you go once, like, so the C and B, right? It's a big long one, but why is it not considered a C if it's like that?
This is a CH. It's
That's a
skinny.
C, yeah. And isn't that also skinny?
It's at 1700, so it's a C double bond O.
Oh, yeah.
Only the thing at 3000 is going to be a CH. So the width and the location are the two things I have. The width, the location, and the strength, how deep it is in the picture.
CH kind of like in the beginning of 3000, like it goes only up to like 3000.
There it is at 3000. Like, what more do you want?
Exactly.
Let's see. Let's keep going. Which of the following could be ethanoic acid? This one or that one, and why? Okay, so I'm hearing you guys think it's the one on the right. What is this one missing? It's missing the C double bond O. What else is this one missing? The very broad of the Ku as opposed to just the broad of the OH. So this is an alcohol. This big one is a Ku.
Wait, could that one also be like the NH one because it has 2 bands?
No, this is a CH band. I can see all that structure. The NH actually looks different. And again, I don't expect it ever to come up. So
Oh,
I'm going to pray.
So what would that first one be?
This would be an alcohol. And again, you can imagine that there's a peak around 1200 that could be a CO bond, but which one is it? I have no idea. I can't use that very definitively, but if someone made me point to it, I sure would draw an arrow and hope. So it's going to be this one, very broad, and the C double bond O.
So very broad, like can encompass like COOH.
An absorption occurs with a wave number of 3000 wave numbers. Calculate the wavelength of this absorption. You might recall that this is wave number and it's equal to 1 over wavelength. So lambda would be equal to 1 over 3000 centimeters to the minus 1. Plug it in your calculator, get an answer, I don't care. I've never seen numbers like this, but I mean, let's go. No. You need to know that a wave, I mean, it tells you the wave number is a reciprocal centimeter. So you just have to take the reciprocal of it. And so I get 3.33, obviously, times 10 to the minus 4 centimeters. And I could try to make that look better if I was so inclined. I don't feel like you guys look particularly inclined. It didn't give me units I had to use. What do you want?
What's the
reverse or reciprocal wavelength. That is the unit in which all of IR spectroscopy is done. Lambda is just the wavelength, the wave number. How could infrared spectroscopy be used to distinguish propin 1-all from propin 2-all? We would have to look at the fingerprint. We can't look at any structures in there and be sure, but if we had a table that showed us spectroscopy, I'm fond of the SDBS, the structural data, the S is Japanese, the Japanese database of spectroscopy. It's very good, we'll go there when we're a little better at this. Which of the following vibrations for carbon dioxide would be IR inactive? So this is one, the asymmetric stretch. Am I changing a dipole? So a dipole is the difference in electronegativity times the length between the carbon and the oxygen. And so this dipole is going to be small, this dipole is going to be big. Now this dipole is big and this one is small. So I am changing the dipole here. Symmetric stretching. They're equally matched. So even though each bond dipole is changing, they exactly cancel. So this one would be IR inactive. Last question, explain why the C double bond O absorption for propanone occurs at a different wave number to the C double bond O absorption for propanal.
All
Al has an OH in it, maybe? No, I know,
It's like an H. And he told you how to see it. So the difference is the C, the difference is the H.
That is the difference between the two molecules. The only thing that we're doing differently is adjusting the masses slightly differently. So here the mass is evenly balanced, here the mass is off to one side. That will change the frequency. The biggest shift in frequency that you will find to this table is when you throw a benzene in there. So if you put a benzene on this molecule, benzene has a mass of, 72 plus 5 more, 77. We're gonna find that increasing that mass decreases that wave number quite a bit. And so in the small number of cases where they throw a benzene ring in, all of the numbers in the table have to be taken with kind of a significant grain of salt. So a hydrogen is kind of messy, it will change things, and a benzene is kind of messy, it will change things. So again, I said that's like your 60% confidence that it will be in that range. Be brave. Brave. Risk takers, that's one of the might be things you have to do. So learner profile attribute. Easy today, hard today?
I like
It was okay.
Okay, that is IR spectroscopy. I'll take middle.
it exists in my.
I'm gonna post the homework, but you don't have to do anything. I'll post an answer key.
Are we done? Are we done?
We are doing 11.3, which is referred to as the spectroscopic identification of organic molecules.
11.3. Okay, so
We're
this is.
doing 11.3, 21 points, 1 and 2.
I also include the IHG stuff.
IHD is an 11.3, yes.
Is it spectroscopic?
Determination or identification of organic molecules. It's really determination.
So this is topics 11.1 to 3.
Okay, so we have not talked about 1 and 2 this year. We talked about 1 and 2 a little bit last year. We said words about error when you were in the lab.
So this entire class is 11.3.
This entire class was part of 11.3.
I like that sound.
Hmm?
I like that sound.
I wanted to see if anything.
I don't think you have time for math spec, right?
Oh, no. I promise I didn't.
I can go to first period right now and see if anybody's taking a test. Is he worried?